Welcome to the deep dive. Today we're heading out into the cosmos.
hmm
We're exploring some news that's really, shaking things up a bit in the world of exoplanets.
Yeah, those planets outside our solar system.
Exactly. And specifically, these super Earths, turns out they might be way more common than we thought.
Yeah, exactly. And the real kicker here, it isn't just that there might be more, it's where we're starting to find hints of them.
Right.
So for this deep dive, we're digging into a really fascinating recent study. Our mission, if you like, is to understand what this discovery actually means for, well, how planets form and just how many might be out there.
Okay. And our source for this cosmic news,
Yeah.
it's a news article, and it's reporting on a study using the Korea Microlensing Telescope Network, KMT-net.
KMT-net, right. Powerful stuff.
And the big takeaway, the headline grabber, is that these super Earths, they might be hanging out much further from their stars than we usually detect. Like maybe as far out as Jupiter is from our sun.
Which is pretty far.
Yeah. And get this. The study is suggesting, roughly, for every 3 stars, there could be at least one super Earth in that kind of wide Jupiter-like orbit.
Wow. Well, that's a really significant shift in how we've been thinking.
How so?
Well, for a long time, the main ways we found exoplanets gave us a really good look at the inner parts of solar systems.
The close-in stuff.
Yeah, exactly. Much easier to spot planets whipping around their stars really quickly. So our view has been a little biased, maybe.
Okay, yeah, let's unpack that. Why have those closer planets been easier to find? What's the big challenge with seeing the ones further out?
Right. Well, think about the two main methods, the workhorses. The transit method.
Where the planet blocks a bit of starlight.
Precisely. We see a tiny dip in brightness, and then there's the radial velocity method.
The star wobble one.
Exactly, caused by the planet's gravity tugging on the star. Now, both of those methods, they're just much, much better at finding big planets or planets that orbit really fast. A big planet or a fast planet causes a bigger, more frequent signal, a more noticeable dip, a more obvious wobble.
Right, more chances to see it happen.
Exactly. But a smaller planet, way out there, taking maybe years or decades to orbit,
You might only see one transit in like 10 years of watching.
if you're lucky. So it's incredibly hard to catch. And the gravitational tug, it's much weaker, more subtle, spread over a long time, easy to miss in the noise.
That makes total sense. It's like trying to spot a slow-moving barge way off in the distance versus a speedboat zooming right past you.
Good analogy, yeah.
So how did this KMT-net study manage it then? How did they peek into those outer zones?
Well, they used a completely different technique called microlensing. It's pretty cool, actually.
Microlensing. Okay.
It doesn't rely on seeing the planet's light or shadow directly. It uses gravity itself, based on Einstein's general relativity.
Okay, Einstein, space-time warping,
Yeah,
that sort of thing.
you got it.
Uh.
Think of space like a stretchy fabric. A heavy object, like a star, makes a dent in it. And that dent, that warped space, bends the path of anything passing through it, including light from a much more distant star.
Whoa, okay.
Yeah.
So the gravity of a star closer to us is actually bending light from another star way behind it.
Exactly. When a foreground star passes almost directly between us and a background star, its gravity acts like a lens.
A lens?
Yeah, a gravitational lens. It focuses the light from the background star, making it look temporarily much brighter to us.
Like a cosmic magnifying glass just box up for a bit.
That's a great way to put it. A temporary cosmic magnifying glass.
Huh. So how long does this brightening last? Is it quick?
It varies. Could be just hours, could be months. Depends on the mass, the speeds, how perfect the alignment is.
Okay.
But here's the really clever bit for finding planets. If that foreground star, the one acting as the lens, if it has a planet orbiting it, that planet's own gravity adds another little warp.
A smaller warp.
Yeah, a tiny one. And it causes an extra little spike, or like an anomaly in the brightening pattern we see from the background star, a little blip on the main curve.
Okay, so that extra blip tells you there's a planet there orbiting the lens star.
Precisely, even if the planet's tiny or dark. And here's the key thing for this study. Microlensing is actually more sensitive to planets in those wider orbits.
Really? Why is that?
Well, the sort of zone where the planet's gravity can cause that detectable extra blip is further out from the star, roughly speaking. So planets orbiting at distances like Jupiter or Saturn are actually kind of in the sweet spot for this technique.
Wow. Okay, so it complements the other methods perfectly by looking where they struggle.
Exactly. It opens up a whole new region of planetary systems to us.
So this Korea Microlensing Telescope Network, KMT-net, Tell us about that. It's designed for this.
Yeah, KMTNet is a really smart setup. It's 3 identical wide-field telescopes, but they're spread out across the southern hemisphere.
Where?
Chile, Australia, and South Africa.
Ah, so they get continuous coverage.
Pretty much near continuous, yeah. They all stare towards the center of our galaxy, the galactic bulge.
Because there are just tons of stars there.
Billions of potential background stars. That's the best place to hunt for these microlensing events. So the researchers took all this KMTNet data and carefully analyzed those little light curve anomalies.
The blips.
The blips, the tiny signals that gave away the presence of these hidden planets.
And what was the big find? What did the analysis actually show?
Well, like you said at the start, the huge thing is the strong evidence that super Earths, bigger than Earth, smaller than Neptune, they aren't just stuck close to their stars. They seem to be pretty common out at distances like our gas giants, Jupiter and Saturn.
Right. And you mentioned a quote from one of the researchers, Andrew Gould.
Yeah, Andrew Gould, he put it nicely. He said, scientists knew there were more small planets than big planets, but in this study we were able to show that within this overall pattern there are excesses and deficits. It's very interesting.
Excesses and deficits. So it's not just a smooth trend of more small planets everywhere. There are like peaks and valleys depending on the distance.
Exactly. The distribution is more complex than we might have thought. But the really striking part is their estimate of how common these outer super-Earths actually are.
This was the 1 for every 3 stars thing.
Yeah. Gould also said their findings suggesting these massive worlds are extremely prevalent across the universe. Their math points to about 1 super-Earth for every 3 stars having an orbit similar in length to Jupiter's.
A Jupiter-like orbit. So
Yeah.
taking, what, 10, 12 years to go around?
Roughly, yeah. A long, slow orbit compared to the hot Jupiters we found early on.
1 for every 3 stars. That just feels like it completely redraws the map of, what a normal solar system might look like.
It really does. It suggests our earlier picture, heavily based on finding those easier to spot inner planets, was just, incomplete. Significantly incomplete.
We are missing a huge chunk of the population.
Precisely. Our estimates of how many planets are out there were likely skewed low because we couldn't easily see this whole group of planets. Microlensing, thanks to networks like KMTNet, is basically showing us there's this vast population of mid-sized planets in wider orbits that we were mostly blind to before.
Like finding a whole new type of animal in a jungle we thought we knew.
Yeah, or like you said before, a whole new continent on the cosmic map. It's that significant.
So, stepping back. What are the big implications here? What does this revised picture really mean for how we understand the universe?
Well, first off, just the sheer number of planets. It probably means there are far, far more planets in our galaxy and the universe than even our recent estimates suggested.
Because we found this whole new category that's apparently very common.
Right. If these super-Earths in Jupiter-like orbits are truly this prevalent, then you can basically assume almost every star has planets, and a good chunk of those might be these distant super-Earths. It just massively increases the potential planetary real estate out there.
Okay. And I know the study itself wasn't about habitability, right? They weren't checking if these planets have water or anything.
No, not directly. Microlensing tells you about the mass and the orbit, primarily. Not usually about atmospheres or surface conditions. That's much harder.
But it's hard not to think about it, isn't it? We've just potentially found billions, maybe trillions more planets out there in these further out orbits. Does that change the odds for finding life, even indirectly?
Well, that's the big question for you, the listener, to really chew on, isn't it? While this specific finding doesn't say this planet is habitable, it dramatically increases the number of planets overall.
More lottery tickets, basically.
Kind of, yeah. The more planets exist across all sorts of orbits and sizes, the higher the statistical chance that some of them, somewhere, will end up in the right place, the habitable zone, with the right conditions for liquid water. Maybe even life.
So it broadens the search field, in a way.
It broadens our perspective on what planetary systems can look like, absolutely. It shows there's maybe more diversity out there than our initial observations suggested. And that, yeah, definitely fuels the hope and the ongoing search for potentially habitable worlds.
Okay, so let's try and wrap this up. If we boil it all down, what's the single key cosmic takeaway from this deep dive?
I think the core message is that microlensing, especially with dedicated surveys like KMTNet, is pulling back the curtain on a previously hidden population of planets.
The distant super-Earths.
The distant super-Earths, yeah. Once thought maybe rare out there, they now seem to be surprisingly common, maybe even the norm across the galaxy. It forces us to revise our models of planet formation and frequency.
Okay, so A final thought for everyone listening.
Mhm.
As you look out at the universe, maybe consider this new picture, this idea that super-Earths might be lurking way out there around countless stars.
Mhm.
How does that change your perspective? Does it make the universe feel more crowded, more full of possibility? What new questions does it raise for you about our place in it all?
Definitely a lot to think about.
Indeed. Thanks for taking this deep dive with us.